Hello everyone, in this video we're going to learn about nuclear and particle physics. Let's start with a unit conversion first. We have two quantities that can be used in two different units. The first one is mass. It can be either in kilograms or in U. U stands for atomic mass unit. This is the conversion. Next quantity is energy. It can either be in joule or in electron volt. Next we have the basic structure of representation of an element. We have X as the element. E is what we call nucleon number, which consists of proton number and neutron number. These two are considered as nucleon. Z is the proton number, while N is not stated here, but N is actually neutron number. This is a Z, and this is the N, and this together is A. So in order for us to get the neutron number, we minus A with Z. A as in all. What is subatomic particles, you might ask? It consists of neutron, proton, and electron. So about subatomic particles is that if they are individual, the mass is different than if they are in pack, which is in nucleus. If we sum them up together, you're going to get 4.03186 atomic mass unit. I put here another one, which is mass of electron in also atomic mass unit. Put it here for you. This is just an extra. If they are in a nucleus, let's say this is one nucleus, it also consists of 4 subatomic particles. The mass is 4.00153, which is much lesser than if they are individually. So what happened is that the difference is by 0.03033 atomic mass unit, or sometimes you call it as U, or 5.03478 times 10 to the power of negative 29 kilograms. So what is this actually? This is what we call loss, the loss of mass. This loss of mass is actually used to bind them together, because we know that proton and proton together, by right, they are repelling each other, yet they are packed together. In a nucleus, it shows that there must be some sort of energy used to bind them together. And in order for us to get that to that point, which is what we call binding energy, we need to find the mass defect. In chemistry, we have learned that in atom, we have nucleus and also electron surrounding it. So know the difference. If the questions give you the mass of a nucleus, you just times the proton number with the mass of the proton and the neutron number with the mass of neutron, and then you just tolak dengan mass of that nucleus. But if the question gives you the mass of the atom, then you have to add in the mass of electron, where it is times the proton number, because we know that number of proton and the number of electron should be the same in one atom. Then you minus the mass of the atom. Here I have mass of each subatomic particles in kilograms. Now, after we know what is the mass defect for that particular nucleus, then we can convert this mass defect into its energy, which is what we call binding energy, or EB. There are two equations because we have 2 units for mass and 2 units for energy. If the question gives you the delta M in kilograms, you can use binding energy equals to delta MC squared. The unit is in joule. But if the question gives you the mass defect in ANU, atomic mass unit, then you're going to use binding energy equals to delta M 931.5 mega electron volt. So the unit can be an EV or times 10 to the power of 6 electron volt. C is the speed of light, which is 3 times 10 to the power of 8 meter per second. Now let's go to another quantity called binding energy per nucleon, or EB over A. Unit mega electron volt per nucleon. I'm going to give you an example. You have uranium-235, which binding energy is 1783 mega electron volt. And we also have nickel, which is 545.2 mega electron volt. Now, looking at these two numbers, it seems like uranium has more energy. But when we divide them into its nucleon number, we can see that for uranium-235, the binding energy is only up to 7.59 mega electron volt per nucleon. In other words, 7.59 mega electron volt is contributed by each one of the nucleon in the nucleus. But for nickel-62, you can see that it is up to 8.79 mega electron volt is contributed by each nucleon in its nucleus. So in other words, we can see that even though 235 has higher binding energy, nickel has higher binding energy per nucleon. Thus, nickel-62 is more stable. So what is binding energy per nucleon means? It is a measurement of the nucleus stability. The bigger the number, the more stable the nucleus is. When I talk about nuclear stability, it is more on the how hard it is to undergo nuclear reaction. So it is either fission or fusion. Fusion is more on the 2 small nuclei bind together, fuse together to make one new element. While fission is one big nucleus split into 2 different elements, where both of them produce radiation and energy. As we all know that all the elements that we have found in the Earth already been charted in our periodic table, it means that we can also chart the binding energy per nucleon And we can put it in this kind of graph. So here we have binding energy per nucleon versus the nucleon number. So we have three regions. The first one is the fusion region. Then we have the region of greater stability where the nucleon number is around 50 to 80. And we have fission region, which heavy nuclides around 200 to 240, where the binding energy is around this much. They are considered unstable and radioactive and less tightly bound and easy to break because they're too big and they can break easily. So this is called fission region. For the region of greater stability, this is where these elements are very hard to break or to fuse together. So they are basically stable, unlikely any nuclear reaction can happen. The highest is nickel 62, next is ferrium 56. The figures are here. For the fission region, we have three distinct peaks: helium, carbon, and oxygen. They are basically more stable than its neighboring element.